Okay, so let's see some examples on the PowerPoint slide. So better you open the PowerPoint slide with the video so you can switch back and forth to the PowerPoint slide and the video, right? So this one is an animation. It's in slide number 46. So the example shows you a skier. She or he is sliding from this point to the bottom. So this slide is frictionless, and then she enters into a frictional horizontal surface, right? So she starts his motion with initial velocity 0, and the height is, let's take h, right? And so she reaches this spot. Here, no friction. So I'm just going to analyze how we can see the trade between kinetic energy and potential energy, right? So let me take this as initial and final. So the ground is going to be my zero potential energy level, right? So what can I write? Initial energy, total energy is equal final total energy. So a total energy will have kinetic and potential. This has kinetic and potential. So what is the initial kinetic energy? You know, the kinetic energy is 1/2 mv squared. So the velocity is 0 here, so it is 0, plus the potential energy mg, h from the 0 potential level, so it is h height, equals, so here definitely the person will reach with the velocity, so let's write m v final squared plus what is the potential energy here? It is the 0 potential energy level, so mg0. So finally we will have an equation like this. So here we have only gravitational potential energy. Here we have only kinetic energy. So now when you pause this and look at the animation, you can see here the potential energy is maximum, and while the person is sliding, the potential energy decreasing because the height is decreasing. At the same time, the speed is increasing, so the kinetic energy will increase, right? So you can see the trade between both from here to here in the animation, right? My second example is in PowerPoint slide. Give me 1 second. So the next one, number 47. Number 47. So that's a pendulum. So you know the pendulum will oscillate back and forth. So let's see. This is the maximum heights it can reach, right? So we know they become momentarily 0 at these edges. So we know the velocity is going to be 0 here. So what can you say about the kinetic energy? It's going to be 0 at these ends. But here it will pass with a higher velocity, actually, the largest velocity. So 1/2 mv squared, which is actually the kinetic energy maximum. Now let's come to the potential energy. So let's take this, the lowest position is the ground or the 0 potential energy level, so this level. So at the ends, so it's going to be oscillate like this. So let's take these at the end, the bob is at height h, right? So what can you say about the potential energy now? So you can see here this is the zero potential energy. So the potential energy is zero. But this is the maximum height. So the potential energy, which is actually maximum, is mgh. Same as here. So when it oscillates back and forth, again there is a trade between the kinetic and potential energy. So here kinetic energy 0, maximum potential energy. Then the kinetic energy increases, the potential energy decreases, and when it reaches this lowest point, the potential energy is 0 but maximum kinetic energy, right? So these are two examples that we can show the trade between kinetic and potential because the energy is conserved. Now let's go to the slide number 48. So it is a problem or a usual or very frequent multiple choice question. So slide number 48. So there is a tall building. This is the ground. So a person is throwing 3 identical balls. So identical means same mass, right? But with 3 different angles. So the first one will go like this, M. The second one like this, M. The third one, so at different angle to the horizontal, M, right? And another condition is they all are thrown with same initial velocity. So same mass, same initial velocity. The question is rank the speeds while they hit the ground. Right? So what can we say? Let's take just one example. So it's going to be like this, going to hit here. So let's take the height is h. I'm going to do it with in symbols. So let's take 1, 2, 3, just one example, right? So let us take number 1. So what I'm going to do, so the next thing we are going to neglect the air friction. So for number 1, E initial, E final. So you know kinetic, potential, kinetic, potential. So for number 1, if it is with VI initial velocity, I can write like that. It's potential energy mg. So this is my 0 potential level. So from there it's height h. But when it comes at this point, there should be a final velocity, but I do not know, plus the potential energy is going to be 0. So what I can do to simplify, I can cancel the masses. Now I'm going to multiply by 2. So 2gh is V final square. So you can see a familiar equation actually. The V final squared is V initial squared plus 2gh. So when you see this equation does not depend on mass or mass, but even though it has same mass anyway. So the 3 masses, they all have same VI, they all thrown from same h. So the final velocity is going to be same for all. I'm going to give you another work. Suppose the same situation, but now different masses, M1, M2, M3. So now think about what would be the hitting velocity of these three. So try this because these are some usual types of questions in multiple choice. Right? So next I'm going to see another example, so which is titled in the PowerPoint slide. So PowerPoint slide number 49. The title is Platform Diver. So what you can do, pause the video for a moment and go to the PowerPoint slide and read the problem and have a look the diagram, look of the diagram, so it will be easier to you. So once you did that, then you can follow up this. So there is a diver who is climbing from here to the top, right? And then he is diving downward. So this height is 10 meters, right? So that is given. That's the only thing given, right? And another thing given is a diver of mass m. So his mass is m, drops from the board. So V initial is going to be 0, right? So part A is asked, find his speed at 5 meters above the water surface. So this is the water surface, right? So 5 meter means suppose here, so which is 5 meters. So we have to find the velocity here. So I'm going to mark this level as A, B and C. So I need to find what is VB, and I know the initial velocity is 0, right? So let's also take here, this is my 0 potential energy. So what I'm going to do to find the velocity here, I'm going to use my conservation of energy at A and B. So at any point the energy is conserved. So I can write energy, total energy at A is equal to total energy at B. So I have kinetic potential at A, kinetic potential at B. Okay, now let's write. So when you come to A, you know the kinetic energy is 1/2 mv squared, potential energy mgh. So I'm going to write, if it is 0, 0, right? So here V is 0, so the kinetic energy is 0. When you come to potential energy, from the 0 potential, its height is plus 10, so mg 10 equals, at B, the kinetic energy. So that's what we are going to find, mvb squared. This is the question. And the potential energy here, so it is 5 meter above the 0 potential energy, so mg 5. So let's simplify that. So first we can cancel all these masses, and now I can write 9.8 times 10 equals 1/2 VB squared plus 9.8 times 5. So you can simplify this. You can isolate this one side, subtract this term both sides. So you will get 10 minus 9.8 times 5, which is going to be 49. So now VB squared is 98. So VB is square root of 98, which is 9.9 meters per second. Right? So I'm going to write the part B here just to show you everything in one page. So part B asks, find the speed as he hits the water. So we have to find VC. So the same procedure. So I'm going to use it from here at this point and this point. So the energy at A should be equal to energy at C. So you know kinetic, potential. So all this time we have only gravitational potential energy. If you like, you can put this one, but if you know, just you can leave that notation. So VA same as that. So mg into 10 equals, so here it will hit with some velocity c, but what is the potential energy here? It's 0. So now I have these two terms, so I can cancel masses first. So 9.8 into 10, which is Vc squared by 2. So you can solve, so I'm going to skip the detail. You can solve it by yourself. So it's going to be 14 meters per second, right? So I'm going to do 2 more examples, right? So the next example is the same as the slider or the skier, right? But the you will see the difference. So this is PowerPoint slide number 50. The title of the problem is hit the ski slopes. So as earlier, you can pause this video, go and read the problem. You can see the image or the diagram and then come back again, right? So the problem is similar to an example we did earlier. There is a skier who slide from a position A to B, and there is a horizontal surface which is actually rough, right? So what else they have given? This height is 20 meters and okay, so he starts from rest, so VA is 0, the mass is not given, and here no friction, here the mu k is 0.210. So the part A is find the skier's speed at the bottom. So they asked what is VB, right? So from here to here, no friction involved. So we can use conservation of energy. So as usual, EA is equal EB, and total energy means kinetic and potential, right? So let's take at A. So you know how to do that. Here start from rest, so velocity is 0, so 1/2 mv squared is 0, potential energy mg20, and here that's the velocity we are going to find, and the ground is my 0 potential energy, so 0. So now I can cancel this. Now I can plug these values, so it's going to be, if I multiply by 2 both sides and plug the value for G, so this is going to be your VB squared. So you can multiply this and find the square root. You will get 19.8 meters per second. So that's the velocity here. But the second part, or part B, they asked how far does the skier travel on the horizontal surface before coming to rest. So let's see, let's assume that at C, the velocity becomes 0. So in the diagram they have given this distance as d, so let's use that. So we now know what is VB, which is 19.8, and here it is 0. So can we use conservation of energy here? No, because it involves frictional force, which is non-conservative. So to find D, we have to go back to work kinetic energy theorem, right? So let me draw a quick free body diagram while the person is moving here. So we know there is a gravity, normal, and the only force acting, the other third force, is the frictional force. So he is moving this way, it is in the opposite direction. So the work done is going to be by mg normal by Fk. So you know change in kinetic energy. So we usually write final minus initial. So I can write half m v final squared v initial squared. So we know these are zeros. So we have only Fk, which is a negative work done because the force and the displacement is opposite. So Fk d equals 1/2 m. So the V final is 0 minus V initial is 19.8 squared, right? So now we have to find Fk. Let me find it here. So we know Fk is mu k n, and since it's horizontal, n is equal mg, so mu k mg. So let me plug that here. D 1/2 m. So there is a negative. I'll write it in front of that. 19.8 squared. Now you can cancel m. We can plug these values. So mu k is 0.210. G is 9.8. And D, that's what we want to find. Minus 1/2 19.8 squared. So now we can cancel these two. So you can find D. So you can rearrange that. So I will leave it to you to solve this. And the answer is going to be 95.2 meters. So when you do it by yourself, check whether you will get this answer. Okay, so this is an example which involves conservation of energy and work kinetic energy theorem to show you where you can use conservation of energy and where you can use, or you have to use, work kinetic energy. Now I'll come to the last problem. So which is going to involve a spring, right? So let's see this problem. So the problem is in slide number 51. The title is a horizontal spring. So this is going to be my last one. Okay, so as earlier, pause the video, go back to the problem, read it, and then you can come back. Okay, so here a horizontal surface, frictionless, no friction. So initially let's think, okay, let's define a point when the spring is at equilibrium, right? Or x, okay, x is 0. It has a block, so the mass of the block is 5 kilogram. The spring constant is 400 Newton meter, frictionless surface, and the question, the situation is they extend the spring, right, at a distance. So this is your x is equal 0. So this distance is x 0.05 meters. So what they do, they pull this and then leave the hand, so it will move back and forth. So the question A is the speed of the block when it reaches first the equilibrium point. So when it comes here, so when it reaches first at this point, so they ask what is the velocity here. So let me mark the equilibrium as O and this point as A. So they are asking what is the velocity here when it is come back in this direction, right? So here the things that we need to remember is the spring that we always use is a light spring. So its mass is 0. And in this particular problem, it's a horizontal spring. So in the horizontal, the potential energy is going to be same all the time, right? No change. So keep that in mind. So let's find, so they ask what is the velocity at O when it reaches first here, right? So here no friction involved, so I can use conservation of energy. So initially at EA should be equal to EO. So now same kinetic energy, potential energy, kinetic energy, potential energy. But the difference here is this system involves two things. One is spring, second is the block. So we have to think about spring and the block. So I have two more branches here. So I'm going to write spring, block, spring, block. So because for each of them you have a kinetic potential, kinetic potential. So spring, block, spring, block. So if you write this way, you will not miss any of them. But you will see most of them are going to be 0, right? So let's come to this. So now let's substitute the values for the kinetic energy spring, kinetic energy block like that. So when it is come to kinetic energy of the spring, so you know 1/2 mv squared for any object. So you can see that it is the light spring always and the mass is 0. So for the spring, since we always going to have a light spring, the kinetic energy of the spring is going to be 0 always, right? So let's take that one. So kinetic energy of the spring 0, and at A the kinetic energy of the block. So we pull that and leave it here. So at this point the velocity or speed is 0. So it's going to move back and forth. So at these edges the velocity or speed is going to be 0. So for the kinetic energy of the block at A is also going to be 0. So this is the kinetic energy of the system. Now let's come to the potential energy. So the spring, you can see it is stretched. So it has a potential energy which is 1/2 k. This extension, so let's put x squared right now, plus the block, it's always, let's take this horizontal is the gravitational potential energy 0 level. So this is going to be 0. And now at O, at the equilibrium, but it's going to move with the velocity. Okay, let's come to the kinetic energy then. The spring is 0 since the mass is 0. The block, you have to put 1/2 m. That's the question. What is the speed here? So let me put VO squared. So that is the kinetic energy. Now let's come to the potential energy. So at equilibrium, no stretch or no compressed. So the potential energy of the spring is going to be 0. and or in other words the x is going to be 0, so 0, and the block, it has a gravitational potential energy which is 0. So you can see so many components are 0, so you will have at the end only this is equal to 1/2 mvo squared, right? So now we can cancel this 1/2, and if you plug the values, so the k is 400, the x is going to be 0.05 at A, equals, the mass is 5 kilograms, V naught squared. So you will get the V naught is square root of, so you can solve this or use your calculator to solve this. You will get 0.447 meters per second. So you might think why I am writing all these and then put zeros. So that's give you the whole idea, right? So we are not missing any kinetic or potential or the two objects in the system, right? So now let's see part B. So it's a little more complicated. So in part B, it's asked find the speed when x is equal 0.025. So you can see if I draw the diagram again, so let's think this is the equilibrium position, x is equal 0, right? And initially it is stretched to x is equal 0.05. So then they leave it, it will move here 0.05 and then like this. But the question in part 2 is when it is at x is equal half of this length. So this is x is equal 0, x is equal 0.05. This is 0.025 meters. So we have to find the speed here. So earlier we put this as O, this as A, and now let's put this as B. So the question is what is VB, right? So the same as, let's write the equation, or the energy at A is equal to energy, total energy at B. So let me write the kinetic and potential quickly. And this is for the spring block, spring block, spring block, spring block. So as earlier, kinetic energy of the spring always 0 because the mass is 0. Kinetic energy of the block is 0 because it starts here. And the potential energy of the spring here is 1/2 k 0.05 squared plus the potential energy of the block 0. Now let's write this part here. So at B, the kinetic energy of the spring 0, but the question is that 1/2 k, sorry, it's the kinetic energy. So let me write it again. So the kinetic energy of the spring 0, the kinetic energy of the block here is 1/2 mvb squared, right? Now let's come to the potential energy of the spring here. So it is extended by this length, which is 0.05 minus, oh, I think they have given the coordinate, so this length is 0.025, right? So 1/2 k 0.025 squared, and for the potential energy of the block is 0. So if I rewrite this, I have 1/2 k 0.05 squared equals 1/2 mvb squared plus 1/2 k 0.025 squared. So now I can plug the values. So the k is 400.05 squared, mass is 5, the speed that we are going to find, k is 400 and 0.025 squared. Now let's subtract this part both sides. So then divide by 5. So you can do the steps one by one, but I'm doing them quickly. 400 negative 0.025 squared divided by 5. So you can solve it. Take the square root. You will get VB as 0.387 meters per second. Right? So here the important point is when the kinetic energy is 0, when do you have kinetic energy? When the potential energy is 0. So when you do understand and then do it by yourself and check whether what you wrote here is correct, then you could do any problem. So these are the examples I like to show here. So the rest we can do it in class, and also you can practice at home. Right? Thank you.